What's up, Crypto Crew, and welcome back. Or if this is your first time, I'm Captain Crypto Might, actively escaping the matrix, scoping out the crypto ocean. So if you like your odds, get on the boat, stay up to date, thumbs up, and join the hunt.
What other cryptocurrency should you buy? What's the next Bitcoin? Well,
Crypto Crew, why is Kaspa called Bitcoin 2.0? Because unlike BTC, Kaspa has solved the trilemma. It is secure and fully decentralized, like Bitcoin, yet unlike the granddaddy of all crypto, Kaspa has solved the issue of scalability. This is a rather complex issue. So in today's vid, you will learn a lot about Kaspa's ability to scale. Kaspa's open source researcher and developer, Michael Sutton. If you want to see the full video of his presentation at the Kaspa in Enterprise event, check out the link in the description box below. Shout out to the Kaspa Kai's YouTube channel.
We have a world where the protocol no longer limits the ability of the system to scale. Does that mean we can infinitely scale to any BPS or TPS? The answer is obviously no. You can't infinitely scale because we have another value. It's called decentralization. So we don't want any a participant in the peer-to-peer network to have to buy the most expensive hardware in the world. We want to keep it affordable. We want it to be able to run on commodity hardware. So that's a constraint. We have a given budget or we look at typical systems and we want them to be able to run Kaspa. And then you still want to scale. So how do you scale given some resources? Scaling up to the hardware limits is what I call HPC. Usually when you say high performance computing, it means like a world of supercomputers and all that. But I'm referring to the aspect of high performance coding approaches, parallelism, like actually using a classic system of computer with 8 cores, 16 cores, and utilizing it full capacity. So you get this world where everything you optimize either helps throughput, you either increase the TPS of the system because you optimized, or you lower the barrier to the cost of the hardware. So as a computer scientist, I look at cryptocurrencies. The way I see them up until now, up to Kaspa, is it's an intersection of 3 different research domains. Now, the first one is cryptography. It's the world of basic utilities and primitives that allow secure operation, like PKI is a public key infrastructure. So only if you had the private key and you signed the transaction, it can be verified by anyone else that you're the owner of the funds. And it's unrelated to the consensus system you use as a DLT. It's a cryptographic primitive, a result of a lot of research, which helps us create PKIs. Cryptography is also, you can see it also in mining. Proof of work is based on the fact that no one can guess what nonce or what number would bring you the target block. You have to solve the puzzle, and it's based on hash functions being irreversible. And that's a very classic, basic cryptography primitive that all of proof of work is built on that concept. Cryptography, people can be experts in cryptography. It's a completely different research domain. And cryptocurrencies use cryptography. But they also need consensus, which is another research domain. Having a distributed system, being able to reach agreement, to have settlement, to agree even though you're a decentralized network. And proof of work consensus is actually just a new child in this domain. It's been going on for decades. So it's called the double spend problem. Say you have a bank account and you have like 1,000 euros in it, and there's no you cannot be in minus. So you have exactly that amount, and you can only use that. And you and your wife go to 2 different ATMs and 2 different cities, and you both click the 1,000. You want to pull 1,000, and you both click the final button at the same second. One of you gets it, the other will get an error. It depends on the request that got first to this central database somewhere, and a mutex in the code that got that request first and captured this amount and gave it to one of the requests, and the other one will fail. Inherently, it uses the fact that there's a central point that makes decisions, because the system doesn't care if you or your wife get the 1,000. It just cares that not both of you get it, and that it's consistent. That's what we want to achieve in consensus without this centralized point. We want to know that there's a distributed network, and different parts of the network might be seeing, and you still want the system to converge on one financial state. Being able to have this fast network, especially at making the decision of convergence in a matter of seconds, like Kaspa does, is like the thing you're like, okay, how does this happen? How does it make sure that it's not confused? How do they all know to agree? What guarantees that? And that's why it takes like a security proof in a paper to actually prove that no attack strategy can manipulate this decision. The proof has to cover all possible options of an attacker. That's why it's not so easy to prove consensus and protocols. The third element is Shai touched on this, algorithmic game theory, what we call mechanism design, like designing systems in a way that each rational player would do what's good, best for him. If you design the system in the right way, you want it to operate well when each actor is acting in its own good. People are rational. You want them to make the right decision. So the mining system is one primary example of such a dynamic. The money supply goes to the miners. So their rational strategy is to mine fairly and do the right thing. And the benefit for everyone is the security the system gets from the collective mining effort. In a way, for us in Kaspa, we're now mostly at the third stage of research for when we're thinking about the future problems like MEV, oracles, fee markets, stuff like that. That's where most of the research will go. But I'm here to focus on the fourth dimension that I mentioned, high performance. So my personal perspective is that I met Jonathan also at the Hebrew University in 2018. And I was doing my master's in HPC, high performance computing. I didn't touch consensus research at that point. So I also had vast industry experience in programming and leading groups. And I was doing HPC research, like running complex irregular problems and hardware with multiple GPUs. How do you manage that hardware beast? And I was everything I touched was graph algorithms based. So the DAG is a type of a graph. So that's another connecting point. But I feel like Kaspa now is in this unique place, intersection point between of high performance, system engineering, system research, and being able to give value to a real world currency like Kaspa and allow it to scale more and more. We're not at the limits. I mean, it's an evolving, hardware gets cheaper and gets more capable. So here enters Kaspa on Rust, also known as Rusty Kaspa, like the mature Kaspa. RK was an initiative started by myself 2 years and 2 months ago. And it was an effort to rewrite, optimize, and fully redesign Kaspa's peer-to-peer node to the extent that it can run 10 BPS and more. Original node that was ran by Kaspa when Kaspa mainnet launched was written in a different language and with a different kind of architecture, which was monolithic. Every moment in time, it does one thing mainly in terms of the consensus layers. There was a lot of activity in the communication layers, but the core consensus engine, what we call, used to do one operation at a time. Another thing turned out to be very challenging when we first launched 10 BPS was the real-time relay, the broadcasting of 10 blocks per second. So you have 1 block per second, and it takes about a second to propagate. So the system is more or less, there's no need to tightly manage all aspects. But when you go 10 BPS, usually the propagation time is more like 500 milliseconds, 1 second. So you're producing more blocks in this period of time. And that, making this structure converge all the time and being tightly connected, that what is required from GhostDAG to be secure, takes a lot of analyzing and tightening this interaction and making it perfect. So I kind of want to share what our guiding principles are, how we think about problems. So Kaspa was designed with the BTC ethos in mind, being a thin verification and settlement layer for peer-to-peer action, transactions, money. We don't want to be a computational layer. We want to keep L1 nodes running commodity hardware. We don't want to have 3,000 transactions, which each can be a complicated smart contract operation that needs to be run and creates state and a whole bunch of activity. So modern technologies actually allow us to be fast, blocks per second. It's what we call the frequency of the system. How fast does it respond? Jonathan once said, we want our internet money to be fast. We want to ping it and to be ponged. We don't want to wait for 10 minutes. We want it to work, to be instant. 100 milliseconds, 10 BPS, which means average block time is 100 milliseconds, and known to be the fastest response a human can recognize. Using the GhostDAG line of research. GhostDAG is a paper you can read the first 2 pages. It's intuitive, it clicks, almost like when you read Bitcoin's paper. But it's a fruit of a line of research, and some of The ideas which produced it originally, like Ghost, which is different than GhostEgg, are not really so secure. They can increase throughput, but they have a liveness problem and stuff like that. So it was a thought process that you can see in the line of research Jonathan put out from 2012, I think, to 2018, with a group of researchers in the Hebrew University. And GhostEgg is just the end of that, not the final stop. But GhostEgg allows us to be fast and to be wide, to have throughput. We can scale, and with that, we don't compromise security. Kaspas Goal is to become the ultimate sequencer, in a sense. You want a fast system with thousands of transactions per second, converging on the order, very fast. As a user, that means you can improve your transaction. You can be certain about the transaction you've just sent faster. You also want it to be fair, and that's where MEV resistance comes in. And that's why we think that even though smart contracts where the MEV activity will go on are actually at the layer above, and if we design the system properly, speaking of mechanism design, we can make a system where the ordering is fair in terms of minor extractable value. High BPS, we think about it as a frequency, as fast, and throughput. It gives you throughput. If you fix the amount of transactions the block gives you, and you increase the block rate, so you get more throughput. It somehow happened that high BPS creates a new surface in terms of fairness and the possibilities of design space. It's a known problem of how do you provide external data on chain. You have a smart contract that depends on the state of some out-in-the-world variable that is influenced by real-world events or users engaging it. And then you need some trusted setup sometimes to report the state of this, the price of this token. And the smart contract depends on that. By using this high BPS and creating voting systems where all miners of a round of 10 blocks vote, and you run logic in a way that if a miner deviated from the collective outcome, it gets penalized. So you incentivize correct reporting, and you can create a system where you can actually become an oracle, trusted oracle for external sources, actually, through this mechanism on chain.
Crypto crew, all is coming together for Kaspa. It's just a matter of time and adoption. If you are invested in Kaspa, I suggest you hold or buy the current dip if you can. He that is slow to wrath is of great understanding, but he that is hasty of spirit exalteth folly. Fix your mind before you get to the grind. And with that said, let's continue to escape the matrix. Let's continue to be on the lookout for the next big thing here on the crypto ocean. Grow in grace, and let's make some crypto waves. Say I.